you very much, Marion. I'm very happy to be here presenting this work. As you said, my this topic is relatively new, or not relatively new. It's very new in my agenda. So I'm learning the literature as I work on it. Luckily, I have two co-authors that are experts in the area. So the paper is joint work with Tina Zhang from UC Davis, a student on the market. So I'm advertising her. If anybody is looking for a very good student to hire, Tina is a very promising researcher, and Ester Camiña from Universidad Complutense de Madrid. It seems to me that she's around.
Yes,
Uh,
hello.
Hola, Esther. So in case that's good, because in case there are any very difficult questions, I will just pretend that my microphone is not working and let Esther deal with the challenge. Um, okay, so let me go very quickly to the motivation, and the first slide is just to establish notation more than anything else. Suppose that we have a couple of sets W and M. A matching between these two sets is a one-to-one correspondence that assigns to each element one and only one element of the other set or itself, and it's of degree 2. So if A is matched with B, B is matched with A. That's the first thing that we learn when we do matching theory. And just for notation, we're going to refer to W as the set of women, M the set of men. Every time you see a little W, it's going to be a woman. Every time you see a little M, it's going to be a man. And every time you see an A, I'm going to refer to an A as an agent. It could be either a man or a woman. Okay, so women are going to be W, W prime, W double prime. Men are going to be M, M prime, M double prime. Agents are going to be A, B, C. Okay? Um, so this is the definition, and typically in economics, the second thing that we learn when we learn matching theory is the following. We take as the main solution concept for matching theory the concept of stability. So the way the theory is constructed is that we take the set of men, the set of women, and then for every agent, we assume that there exists a preference profile, a preference, a ranking over the agents of the other set, of the other gender, plus themselves. And then we define stability of a matching with respect to those preferences. Okay, so as economists, we take the problem, we endow the agents with preferences, and we define some sort of equilibrium based on those preferences. And it's a beautiful, well understood theory, and every one of you knows much more about this than I do. We know that stable matchings have some really, really good welfare properties. The theory is really uh, well developed, and the most salient thing to say is that the set of stable matchings of a marriage market is the core of that market, and then many, many more interesting properties. So I'm going to say, and I hope this is not controversial, that this is the starting point in matching theory from the point of view of economics. The concept of stability, and it's the dominant concept 64 years later. Now, it turns out that before Gale and Shapley came with this definition of a solution concept, mathematicians had given a solution long before. So there is a work in computer science that defines an alternative solution for matching theory. Uh, and there is a big difference in approach, which is that in this literature, they don't endow the story with preferences. Instead, they say, let's imagine that for each agent A, there is a set of people of the other gender, and they call them these other people their acquaintances. So the acquaintances of agent I are the set A sub I. And the idea is that these people are the only people with whom agent A can be matched. And they say that a matching is perfect with respect to the profile of these acquaintances if every individual is matched with one of their acquaintances. And of course, this becomes a difficult problem because you cannot pick just one acquaintance, because then if you do that, you may run out of acquaintances for somebody else down the road. So it's a difficult computational problem to have a perfect matching. But we're talking about very, very clever uh, work. It turns out that the perfect matchings have very nice computational properties, in the sense that computer scientists have been developing uh, very efficient, not, I'm going to say the word efficient without any formal meaning. They have developed very good and efficient algorithms to compute the set of all perfect matchings given a population of individuals, and for each individual, one set of acquaintances. So these, in principle, are two separate strands of the literature. Gale and Shapley did not use this literature as far as we can tell. And the set of acquaintances in whole, which are the main fundamental, they did not attempt to relate them to any preference profile. And then, of course, we already know that Gale and Shapley have very good welfare properties. Whole, the results in computer science are very good from a computational point of view, but each of these literatures, I would say, lack the beauty of what the Earth theory has. So, for instance, if all you have is a perfect matching with respect to a set of acquaintances, you cannot talk about welfare. An economist cannot say anything about welfare if we don't know anything about the agent's preferences. And at the same time, we know that Gale and Shapley have some computational challenges, or the concept of stability has some computational challenges. And let me be clear, we know that finding one stable match is very easy. Later on, people have found that finding some stable matchings is not much harder, but finding all possible stable matchings can be complicated, and there is no obvious algorithm that does it efficiently. So our starting point is the observation that there are these two strands of literature, one that works very well from the point of view of computation, but is less useful for an economist because it doesn't allow us to say anything about welfare. The other, which is very good from the point of view of welfare, but still poses some computational challenges. So what we do in this paper is to try to link the two literatures to see if we can exploit some of the results that computer scientists have been obtained for perfect matchings in a context that is related to preferences and to stable matchings. So what we're going to do, if you want it in a nutshell, is that we're going to microfound a set of acquaintances for a perfect matching from the point of view of Gale and Shapley's preferences. And then once we do that, we say, okay, now we have very nice computational properties. Where do the welfare properties take us? And the exercise is an attempt to make the point that a lot of good welfare properties survive once we do our exercise. Not survive fully, but in a weaker version, they survive. So that's going to be also my goal for the talk. I'm going to try to convince you of the conceptual beauty of a new definition of solution. And then hopefully I will have time to show you at least one of the properties that survives in a weaker version. in some detail, and then after that, I'll tell you that there are some more properties that survive. Uh, in some sense, the main contribution of the paper is a definition. We also have results, yes, but if we spend the whole talk discussing about the solution, and at the end you have not destroyed it, I will be happy with the feedback, because it is, if I cannot convince you that this is a solution that makes some sense, then the results are going to be even less interesting. So let's go to the main point. What we do in order to have a new solution for concept for stable for matching theory is we think what behavioral economists would find most natural, which is the following. We know that in Gale and Shapley, people go after the best person that they can convince to match with them. So a matching is not going to be stable if a man and a woman know that they can match each other and be better off than with the people that they're matched uh, at the moment. So every man and every woman is acting optimally in the sense of looking after a better match for themselves. We're going to call that these agents are optimizers. They're always trying to get the best match for them. Now, we know that in behavioral economics and also in psychology, there's been empirical work that shows that many people are not optimizers. Many people in real life are what Herbert Simon called satisficers. So the difference between a satisficer and an optimizer is that a satisficer is not looking after the best possible choice that they can make, or the best possible outcome that they can make. Satisficers like simplicity, and therefore they are happy to achieve an outcome that they consider to be good enough. It need not be the best outcome, but if they think that the outcome is good enough, they're happy to settle for that. Okay? So instead of looking after the best, they look after something that is good enough. And there is even tests known in psychology. There are personality tests that can classify a person as a satisficer or an optimizer. Out of curiosity, I did it, and to my disappointment, I am somewhere in between. But it turns out that many people can be classified as satisficers or as optimizers. And this classification has been used in contexts that are very relevant for what we're trying to do. So, for example, there is a study that classifies a bunch of people between satisficers and optimizers, and then they compare how these people behave in dating sites in real life, not an experiment. They go and see how these people behave in, I don't know, Tinder or whatever, one of these dating sites. And what they find is that satisficers flirt less, they search less for potential partners, they exit the platform faster than optimizers, so they get matched, they settle faster. And then, of course, this is modern life, so people after a while go back to the platform. Satisficers tend take longer to go back to the platform than optimizers. So optimizers are hit on everybody that is around, take a very, very long time to think that they have found a good match, and then very quickly they, I guess, are disappointed by that match and go back to the platform. In same exercise, not in dating, but in job searches, people have found that satisficers stay longer in the search process for a job. They end up accepting lower wages, so they settle faster for offers that are less good than satisficers would get. But interestingly, they regret less their offer. So these are people who go on the job on the search, they find a job faster. It's not as good a job as optimizers get, but they feel more satisfied. They feel happier about the job that they get than optimizers do, even though optimizers get better jobs. So there is a behavioral difference in context related to matching between satisficers and optimizers. And then the last point is a little bit different. This is not an empirical observation, but there are papers in computer science that are trying to see what happens if in Uber or Lyft, these rideshare apps, the current setting is algorithms that always try to look the best match for rider and driver. And they claim this is computationally very, very hard, and it costs the platform a lot of computational costs to be trying to have these optimal matchings between riders and drivers. And they are suggesting that the way to go about this would be to define what is a good enough match between a rider and a driver, and try to let the platform find good enough matches for everybody instead of optimal matches for everybody, to reduce the computational burden on the platform. So this gave us what we think is a language that we could use for our definition of a solution concept, which is that we're going to take preferences as in Gale and Shapley, and we're going to come up with a definition of what these people, each of these individuals, would consider to be good enough matches. We use our definition of good enough to construct the acquaintance sets of Hall's theorem, and then we define a matching to be satisficing if it is perfect with respect to the set of acquaintances that results from our definition of good enough matches. Does this make sense? Okay, so that is going to be our goal for the paper. So let's start with the canonical setting in economics. So we have the set of women, the set of men, and for each individual, we're going to have preferences PA over the set of agents of the other gender and themselves. And as is usual in the literature, to avoid complications, we assume that everybody has strict preferences over the other gender. So these preferences are going to be an order over the union of the other set and the singleton of the individual, him or herself. For the talk, not for the paper, but for the talk, I'm going to assume that there are the same number of men and women, and for every couple of a man and a woman, the man is better for the woman than being by herself, and the woman is better for the man than being by himself. So in the language of Gale and Shapley and Roth and Sotomayor, we're going to assume that every agent of the other gender is acceptable to each agent of a given gender. Every man is acceptable to every woman, and every woman is acceptable to every man. This means that when we do stable matchings, we don't need to worry about people being left unmatched. There are not going to be any single people in our settings. That's just that simplifies the arguments a little bit, but it also simplifies the explanation big time, which is why I'm doing it in the presentation. Okay, now we
So
know
there's a
that.
question.
Yes.
And there's a question in the chat. So Bebertan Tuan, who defines the set of acquaintances? Are they taken given or agents report them?
So we are going to define the set of acquaintances according to the preferences. So if you give me, I don't know who asked the question, but if you give me 30 seconds, we're going to see what the set of acquaintances is going to be. Okay, but it's going to be defined from the preferences of an individual. Okay, so this is the definition of a matching. Now we don't have to worry about single people. So a matching is a bijection that assigns to every woman a man, to every man a woman, and it's a degree 2 mapping. So the mu of A is going to be A. A matching is stable if you cannot find a couple MW for whom uh, each other is better than the person that they're married with, the match with at the moment. So there is no MW such that W prefers M to her match and M prefers W to his match, the canonical definition of stability. And we know that stable matching is guaranteed to exist. We know how to find it. That's the deferred acceptance algorithm is going to give you a stable matching. If you run it in a different way, it may give you a second stable matching. So stable matchings are guaranteed to exist in this setting. And then a little bit of language. Agent B is achievable for agent A if there exists a matching in which they are matched together, a stable matching in which they are matched together. So if there exists a mu, stable mu, for which mu of A is equal to B, that means that B is achievable for A. And because of the properties of matchings, if B is achievable for A, then A is achievable to B as well. Okay, this couple, we can say that the couple is achievable, the pair is achievable. So nothing new here. Let me try to answer the question right away. We are going to propose the set of achievable agents as the set of acquaintances of an agent. Okay, so we're going to define, we'll imagine that we look at the set of all possible stable matchings. We look at the set of all possible achievable pairs. I take each agent A and I look at all the agents of the other gender with whom agent A is matched at some stable matching. Okay, these are the agents that are achievable to A, and A is achievable also to each of these other agents. So the way we construct it is that we define the set of acquaintances of individual A to be the set of all the agents with whom A is matched at some stable matching. Okay? This is going to be our definition of good enough in the following sense. At each stable matching, if I am agent Andrés A and I matched with agent B, let's say Beatrice, Beatrice is the best possible match that I can get. She's optimal given what's happening with the rest of men and women of society. Okay, that's optimizing behavior. That's Gale and Shapley. We're going to say that if Beatrice is perfect for Andres in some matching, in some setting, in some description of what's happening in the rest of the market, then we're going to say that Beatrice is good enough for Andres in any case. Okay? So our definition of good enough for an agent is going to be the set of agents that are optimal under some possible resolution of the market. Okay? So with that definition of good enough, we're going to say that a matching mu is satisficing if it is perfect with respect to the family of acquaintance sets that are constructed as the set of achievable agents under the preferences of that market. Okay, so this is the answer to the question that was asked in the chat. The set of good enough agents is determined according to the preferences of each individual, taking into account the preferences of everybody else. Okay? Notice that there is a lot of strategic thought that goes behind the definition of good enough. One possibility would be to say, okay, I'm going to say that if there are n agents in the other side of the market, then the first 5 are good enough for each individual. And then we would have another definition of good enough, and we could define perfect matchings with respect to those sets of acquaintances. I don't know if a definition like that, I mean, a definition like that would not give you the existence of a solution in every possible case. It would be very easy to construct examples where you cannot use that definition of good enough and still get existence of a matching with the property. So here the setting is, let me repeat. Each agent understands with whom they can be matched in some setting where everybody is acting optimally, including themselves and including their partners. And we say that if there exists a state of affairs in which A is matched with B as the optimal person in which B is optimal for A and A is optimal for B in some state of the market, then A is good enough for B and B is good enough for A in any state of the market. Okay? So mu is going to be, oh, this is a typo. This should be satisficing. Mu is satisficing if for every agent there is a stable matching lambda such that the agent would get under lambda the agent that he or she is getting under mu, the match that they're getting. And notice that right away, stable matchings are satisficing matchings. Since stable matchings exist, finding one stable matching is easy, then finding one satisficing matching is easy as well, because you just find one stable matching that's also going to be satisficing. Okay? Now I think it's a good time to stop to see if there are questions. And if I answered the previous question.
Okay, so I have a question. So I
Yes.
guess the worst acceptable person for a man is the one in the women optimal matching and vice versa.
Yes.
But in principle, not everybody who's better than these people must be acceptable, right?
True.
Or is so that kind of goes a bit against the satisficing story because it's not really a cut-off property of acceptability, right?
Yes and no. So we also have that in the paper. We call that weak satisficing. It loses properties, but there is a reason why I don't like that definition, because imagine that I am in one setting and I match with woman 1. That's my best possible matching. In another setting, in another stable matching, I match with woman 3. And there is no setting in which there's no stable matching in which I match with woman 2. Okay? In our definition, the set of acquaintances would be women 1 and 3. The definition that you are proposing is, well, I like 2 better than 3. If 3 is good enough, why isn't 2 also good enough? If I understood the
Yeah.
question. Right. Okay, but notice that it's not a one-way definition. There is a setting in which 3 is optimal for me and I am optimal for her. there is a setting in which one is optimal for me and and I am optimal for her. I prefer that setting to the matching in which I am with three. But if two is not achievable, then yes, I like two better than three. But there is no setting in which she likes me more. In that set, it's not true that she likes me more. There is no setting in which I'm happy to be with her and she's happy to be with me. That's not true about three and one. Okay? So to answer the question, yes, you are right. That would be a weaker definition of satisficing that only looks at people who are better than the worst possible achievable partner. It's a bit um, it's a bit platonic. These people are happy. I'm happy to be with these people. They're not happy to be with me. Eh, it's not. It's a weak concept, but we have it in the paper. Um,
Yeah.
I like this one better, and this one has nicer properties. But we also have it in the paper just to be sure. Did I answer,
Okay.
Michael?
Yes.
Okay. So
A question in the chat.
okay.
Or I think now it's two questions. No. So the first one is it like having dichotomous preferences over achievable agents?
No, and that's a very good question. We're not saying, okay, all these people are achievable. Let's treat them as if they were all of them indifferent and better than everybody who's not achievable. And because that's not what satisficers do. It's not like satisficers treat every good enough option as if they were all of the same quality. They know that there are options that are better than others, but just there is a threshold after which they're happy to accept. Okay, if somebody came and told them, look, you're not getting this, you're getting this, it's also good enough and it's better, they would be happy to take the better option. So no, we're not going to just split the set between achievable and not achievable, and we make all the achievable agents be better than the other non-achievable agents and indifferent between them. The preferences continue to apply, and the set of achievable agents is ranked according to the preferences of each individual. And that's very important because otherwise the welfare arguments would be pretty uninteresting, I would say.
Thanks. And there's a second question in the chat. Both in this talk and in your paper so far, every single agent is assumed to be a satisficer, right? Not
Yes.
like in that empirical study you mentioned where people were classified as satisficers or optimizers.
Yes. Okay, so all the results that we're going to prove, so the answer is yes. In the paper, we only have satisficers. To a large extent, it simplifies notation. And it simplifies the argument because we don't have to consider cases. But I would bet my salary that every result survives with if we split the setting between satisficers and optimizers. So every agent, every optimizer would have to have an optimal agent, and every satisficer would have to be a good enough agent. The results would survive, maybe even in a stronger version, because we could say more things about the optimizers. So we haven't done it. We could do it at the expense of longer arguments. I don't think that it's necessarily more complicated arguments. It would be longer arguments that have to consider cases all the time. But the answer is yes. At this point, in the paper and in the talk, everybody is going to be a satisficer. Okay, so let me see what can I tell you in terms of results. Ooh, okay. Let me skip this because I think I can focus on something more interesting. So let me remind you that of the structure of stable matchings is a very nice mathematical structure. So I'm going to endow the whole set of matchings with a binary relation greater than or equal. And like in every piece of work that we have seen in the literature where this thing is done from the point of view of men, I remind you, I have two female co-authors. So everything in our paper is written from the point of view of the women in the market. So we're going to say that mu is greater than or equal nu if every woman weakly prefers the match that they get under mu than the match that they get under nu. If one woman strictly prefers the match under mu, then we say that mu is strictly larger than nu. Okay, so now we have a binary relation applying to matchings, not to matches, but to matchings. And it's well known that the set of stable matchings, if you endow it with this with greater than or equal relationship, binary relation, sorry, is a distributive lattice. And this makes many welfare arguments be extremely elegant. And just to say what this means, let me just draw a graph that the set of stable matchings can be seen somehow in this way. There is some stable matching at the bottom, which is the matching that all men prefer, a stable matching that all men prefer. There is stable matching at the top that all women prefer. And then the other stable matchings can be partially ordered according to the preferences of all women, in the sense that the higher you go, the happier the women are, and the less happy the men are. If you go horizontally, then they're not ranked. So between, say, rho and sigma, there may be some men who prefer rho and their partners prefer sigma, and the women who prefer sigma, their partners prefer rho. But between let's say rho and nu, all women weakly prefer nu, at least one of them strictly. All men weakly prefer rho, at least one of them strictly. Okay, so this is the lattice of stable matchings. And as I said before, finding this matching at the bottom is very easy. That's the men prefer the deferred acceptance algorithm. Finding this one is also very easy. Finding all of them is computationally hard. Okay? So now it turns out, okay, just let me skip this in the interest of time. We can show that the set of satisficing matchings is not a lattice, but it has a very nice algebraic structure that it is a semigroup. It's an abelian semigroup, so it's commutative. And so something that is particularly nice is that the set of stable matchings is an ideal for the semigroup. We believe that computationally this has a lot of power, but because it's dry and boring, I don't want to make a big deal out of it. Okay, so we know that a matching is stable if and only if it is in the core of the market. So the first result that applies to satisficing matchings is that satisficing matchings they need not be in the core. If they're in the core, they're stable. But there are satisficing matchings that are unstable, so they're not in the core, but at least they are Pareto efficient. Okay? And I want to argue this result in some detail because the argument has the insight that underlies a lot of our other results. So let's go back to the lattice, and all these matchings are stable. Now, there are some more matchings that are satisficing but not stable. I don't want to draw them here because imagine that I draw them here or here. That would kind of suggest that they can also be ranked according to the preferences of women, and that's not the case. Now, if I were to draw them up here or down here, that would suggest that there are women who prefer some satisficing matching over the women optimal stable matching, and that's not true. Every satisficing matching is going to be in terms of bounds for the men and bounds for the women, they're also going to be bounded by mu W and mu M. So I'm not going to try to draw them here, but what we can get from the lattice is that every achievable pair for every agent, every person with whom they are, every person that is achievable to every other person is a matching, it's a match under one of these green matchings. Okay? So I cannot see the satisficing matchings, but I know that in order to construct satisficing matchings, I have to pick pairs that are matched according to one of these green matchings. That's our definition of satisficing. Now, somebody could come and say, look, what you are doing is hopeless because you just told us that finding all the green matchings is very difficult. And your definition of satisficing matchings requires that you know the set of all achievable partners for each agent. So it sounds like we would need to know all these green matchings in order to define our achievable sets, the achievable sets, the acquaintance sets, and therefore the satisficing matchings. Luckily, that's not really the case. There is a theorem by a mathematician called Gosfield that says the following. Look, in this lattice, there exists a path that connects the bottom of the lattice with the top of the lattice, visiting only one of the levels of the lattice. So it goes directly from the bottom to the top. It is easy to find. This one is computationally easy to find. And all possible achievable pairs are found in this path only. Okay? Yes, we cannot see this matching. This algorithm is not going to give us this matching here or this matching here. But even if you ignore these matchings outside the path, all possible achievable pairs can find under a matching in the path. And this is computationally not too hard. It's just you start from the bottom and you start alternating between men and women who chooses, and then I'm oversimplifying, but that's essentially what the Gosfield algorithm does. It starts from men optimal, and then it starts giving the women more and more and more say until they go up and up and up and up until they go to the top of the matching. And it turns out it's a remarkable fact that all possible achievable pairs are going to be found in this path. So from now on, from the point of view of satisficing matchings, we can forget about all of these matchings, which are stable, but we don't need them. All of these matchings are stable, but we don't need them. All these matchings are enough from the point of view of satisficing matching. So from now on, I forget about everything else in the lattice, and I'm going to focus on the Gauss-Field's path. Okay, so I'm going to try to convince you that any satisficing matching is Pareto efficient. Okay? So let me imagine that I have this couple, this red couple that forms under this matching that is very close to the top. And this blue couple forms under this matching that is relatively close to the bottom. Okay? For reasons that are going to be clear in a moment, let me call the red woman, I'm going to call her Karen. Okay? So this woman here is going to be Karen. I don't need to choose a name for this guy. This guy is called Martin Walker. He created the font for LaTeX that does these figures, and he put his own photo in LaTeX. So I just picked it and put him there. So there is Karen and there is Martin. And let's imagine that as an alternative matching, we match the two of them together. Okay, this looks to be at the level of this matching, but it need not be that. Let's imagine that you pick this Karen and Martin, and you put them together as an alternative arrangement. I'm going to try to argue that it's impossible that they're both better off. Okay? That if one of them is happier here, then the other one has to be unhappy on the right-hand side. Okay? Notice that that fact would be obvious if this red guy was Martin, right? Because this guy is very high for um, Karen. If this was Martin, then Martin down here is at a better matching for men, right? So if this was Martin, then the answer would be very obvious. You're moving Martin from a match that is very low in the lattice to a higher match in the lattice. Karen will be happy, but Martin will not. The same thing would be if this was Karen, this woman here being Karen. So now Martin would be very happy to be with Karen, but Karen would be less happy because up there she was with somebody else in a better matching for women. Okay? So let's assume that this guy is not Martin. Let me call this guy John Doe. He's not going to play an important role. So this is going to be an anonymous John. And this is going to be an anonymous Jane. Okay. And all we need to do now is to assume that John is not Martin, Jane is not Karen. Okay. And I want to claim that it's impossible for the two of them to be happier when they are rematched together. So let me assume that Karen prefers Martin to John. Okay, so she is better off at the orange matching than here. Okay, I want to claim that if that is the case, then Martin must be worse off. If Karen is better off, then Martin must be worse off. And there is one person missing in this story, which is who was Martin with in the red matching. Okay, so unfortunately, LaTeX didn't give me any options. I tried to find who is famous to be the most seductive women in the history of humankind. And apparently, there is consensus that Cleopatra was the most seductive woman ever. And then I tried to find an Egyptian symbol for a woman, and this is the best I could find in LaTeX. So let me call this, she doesn't look very good, but let me call her Cleopatra. Okay? So the question, in order to argue that if Karen is better off, then Martin is worse off, is how does Martin rank Cleopatra over Karen? Okay? Because this matching is high, we know that Jane is better for Martin than Cleopatra. Because this is a matching at the bottom of the lattice, then Martin prefers Jane over Cleopatra. Right? What we don't know is how to rank Cleopatra and Karen. But remember that this matching lambda, the red matching, is stable. And we are assuming that Karen prefers Martin over John. Because the matching is stable, it cannot be that Martin also prefers Karen over Cleopatra. Because then that matching would be unstable. They would be better off rematching together, Karen and Martin. So it has to be true that Martin likes Cleopatra over Karen. And he likes Jane over Cleopatra, because this is a lower matching in the lattice. So Jane is better than Cleopatra, who is better than Karen. Therefore, Martin prefers the blue matching over the red matching, and he prefers being with Jane than with Karen. Okay? Carmelo, I don't know if you were celebrating or asking a question.
No, the other way around. She prefers Cleopatra to Karen, I guess. That is the way I think I see the point.
Okay, he prefers Cleopatra to Karen, and he prefers Jane to Cleopatra. Therefore, he prefers Jane to Karen. Okay, so if Karen prefers Martin over John, then Martin prefers Jane over Karen. If one of them is better off with the rematching, the other one is going to be worse off. Okay? Okay, so how does this argument allow us to prove that satisficing matchings are Pareto efficient? So here goes the formality. Take a satisficing matching mu and take any other matching nu. It doesn't have to be satisficing, it doesn't have to be stable, it just has to be a matching nu. Okay? I'm going to claim that if there is a person who prefers nu, then there exists another person who prefers mu. So let's do the following. Let's take the Gauss-Field sequence that goes from the worst for woman to the best for woman and take the highest of these matchings that forms one of the couples of the satisficing matching, and let's take the woman of that matching and the corresponding mu. Okay? This is going to be Karen. W is going to be Karen. And I'm calling her Karen. I don't know if this language has reached Europe. Karen is the stereotype of people who complain even though they shouldn't. So I'm calling her Karen because if there is a person in this society who should not be complaining, is any woman who is at the highest possible matching. Okay, she is put of all the people in this matching, she is the one that is at the best position for women. Okay, let's call that matching I star. It's the highest of these, and which one couple has formed, and the woman of that couple is going to be Karen. Mu of W is going to be John. Okay, so this is going to be Karen and John. This would be the red matching in the previous slide. Now, let's imagine that in the new matching, Karen is matched with Martin, which is nu of M. Okay? And let's imagine that they are both better off. So Karen prefers Martin over John. And let's imagine that Martin prefers Karen over the woman that he would be with in matching mu. This is Jane. And Jane is lambda I of Martin for some I that is supposed to be lower than I star because I star was the highest possible matching. So if Martin is better off, it has to be that he was not with Karen, so he must be at a lower matching than I star. But then that is the point. Lambda I star is stable. So if Karen likes Martin more than John, then it has to be true that John likes whoever he was with in that matching over Karen. This is Cleopatra. Okay? But if Cleopatra was better than Karen and Karen happens to be better than Jane, then this means that matching I star has to be larger than matching I. Sorry, yes, this I'm saying it the other way. Yes. So this means that matching I star, because remember that having a low I is bad, sorry, having a low I is good for men. So if Cleopatra is Martin's matching under I star, and he likes Cleopatra more than he likes Jane, it must be that I star is larger than I. Okay? Because I is a very bad matching, so it must be close to the bottom. But that's a contradiction because we took I star to be the largest I in the matching. Okay, so I don't know if the explanation was very good. We just put into math what was happening in this slide, and the point is that we pick this couple to be at the highest possible matching. There could not be anybody else up here, and that gave us the contradiction. Okay. How am I doing in terms of time, Marian?
3 minutes.
3 minutes. Okay. So now we know that it's stable. Let me just go. Oh, there was a lot of stuff that I'm not saying. Okay, so let me conclude. We have proof here in the seminar. I showed you one thing in some detail, that satisficing matchings are Pareto efficient. I also mentioned that they form a semi-group. So stable matchings are the core. Satisficing matchings are Pareto efficient. Stable matchings form a lattice. Satisficing matches only a semi-group. Luckily, satisficing matchings observe the same bounds, mu m and mu w, that stable matchings. So that's good. We know that stable matchings are majority matchings. If you ask people to vote between a stable matching and any other matching, satisficing matchings are always going to win at least weekly. In the worst case, they tie. Satisficing matchings lose that property. They will always tie against a stable matching. They will not lose unanimously to any other matching. So something is preserved, but not fully. They need not obtain always majority. Oh, I forgot one nice property. When you compare two stable matchings, if a woman prefers one over the other, both of her matches will prefer the other over the one. So there is perfect clash between the interests of the women and the interests of the men across stable matchings. We obtain, for satisficing matchings, a weaker version of that property. If you compare two satisficing matchings, there will be two couples such that in each of these couples, if the woman prefers the other matching, then the man prefers the first matching. Okay? It turns out that there will be at least three people, because these couples could overlap. There will be at least three people, one man and two women, or two men and one woman, who have a complete clash of interests between matchings. Something that we find pretty cool is that satisficing matchings induce truth-telling, not as a Nash equilibrium. We know that that cannot be sustained. That's Roth's theorem. But we can prove that, at least as a rationalizable strategy, satisficing matchings induce truth-telling. So do stable matchings. But we don't lose that property when we go to satisficing matching. And then the last thing that I wanted to say is that satisficing matchings are in some sense, I have to be careful, in some sense, they are easier to compute than all stable matchings. We don't need to design new algorithms. We just pick off-the-shelf algorithms, the Gauss-Field lattice, and then the algorithms that exist for perfect matchings in order to compute all satisficing matchings. To be sure, we do this also for one-to-many matchings, and the results are more or less the same. We're working on many-to-many matchings where things get more complicated, and I think it's time for me to shut up.
So before there was this question on populations with classifiers classified as sacrificers or optimizers. And the follow-up question on this, after your answer, was wouldn't higher order beliefs matter for manipulability than if you have satisficers and optimizers?
I'm going to say no for the following reason. In the paper, we prove that stable matchings induce truth-telling as a rationalizable strategy. So in that case, we would have higher order beliefs that sustain truth telling when you know that everybody else is optimizing. When you know that everybody else is satisficing, is a satisficer, then truth telling is also sustainable as a rationalizable strategy. So you can form beliefs and beliefs about beliefs and beliefs about beliefs about beliefs that justify telling the truth. Okay, so let me take back the answer a little bit. It depends on what each people know about the other people. If people know who is a satisficer and who is a maximizer, then I suspect that everything goes through without any complication. If you don't, and you have to form beliefs about who is a maximizer and who is a satisficer, as far as rationalizability is concerned, I suspect that the result survives because you have to form beliefs about the character of each of these individuals, and if you form the correct beliefs, then you're going to have still the same incentives. So before I said that I would bet my salary on things surviving the presence of satisfying and optimizing agents. Let me take that bet a little bit. I hope that nobody took it. I still think that it is true with more attention put to higher order beliefs, not about the actions of the other agents, but about the character of the other agents, where they're satisfiers or maximizers. I still think that it can work, but now I realize a little bit of a complication that can arise.